we have 2D graphics and we have 3D graphics. So it's kind of one dimensional up. So 2D graphics and 3D graphics. Okay, but in complexity there is no similarity. Means 3D graphics is means many times more difficult to 2D graphics. So that can be kind of experimental. So anyone can see how much the difference is between 2D graphics and 3D graphics. Now in 3D graphics there are library comes from Microsoft also, but we see mainly OpenGL library that comes for the 3D graphics. Now OpenGL is it's a game of vertices. So if I have kind of vertices, then I just think about the vertices and then we talk about the primitives. So it's a vertices belongs to a triangle, or vertices belongs to a line, or vertices belongs to a quad. So if I set vertices and I set the primitive, then remaining is what is the color of the vertices. Vertex position, its primitive, its coloring, and then transformation. So once we do the transformation, then vertex position changes. So after the transformation, now OpenGL rethinks about the vertices as per the primitive. Then it goes for the net to net the shape that it brings. Then it goes for rasterization. Means I have a triangle, and then it got rotated. Okay, so new vertices comes into the picture, but still it is a triangle. So if it is a triangle, then it goes for rasterization. Means it think about the pixel. Now, since I have set the coloring of the vertices, then what would be the pixel color? Okay, at the end, a pixel has the color, not the vertex. So vertex comes into the picture only for the transformation. So whatever the color we assign at vertices, so those colors would be kind of interpolated for the pixel. Okay, there are blink form and Gorward modeling and so many things that comes when lighting comes into the picture. Whatever means we have to think about the pixel coloring. So in basic term, pixel coloring comes from the vertices. Vertex coloring we assign from the outside. So vertex coloring, vertex position, and then transformation. So and then primitive. So once transformation is done, based upon the primitive, rasterization happens. Once rasterization happens, then pixel color is interpolated from the vertices color. So that is the grammar of the OpenGL. Now, question comes is what about lighting? Okay, so based upon the lighting, like we talked about the blink form or Gorward model, then we discard the vertex coloring because it is not required, and then we think about the lighting falling over the vertices, and based upon the lighting we think about the coloring at the vertices, and then interpolation at the pixel level. So then again with the lighting through the vertices we get the pixel color. So that is the concept. Okay, so at the end, either through vertices coloring pushed from external as extensive parameter, or through lighting, through interpolation we get the pixel color. Okay, so that is the concept. Okay, there is one more way then that we get the pixel color, that is texture. Okay, so rather than interpolating the vertex color into the pixel. Okay, now we get the pixel color. So 3 vertices, triangle, 1 point, 2 point. What are the color at the vertices? So those colors we interpolate at the rasterization, and then we think about the pixel color. But in texturing, we have full texture. So that texture color we set as pixel color. Okay, so OpenGL is not physics, OpenGL is not chemistry, and OpenGL is not biology. So OpenGL is pure mathematics. So mathematics, when it happens, it cannot work in kind of much analog fashion. It is digital and it is discrete. So when we think about the texture color to be set as pixel color in the kind of frame buffer, then what is the texture color for each pixel? So that comes into the picture. Now texture, that if you see the texture is another kind of set of textures. Okay, so texture is not kind of smooth or it's not analog. Okay, so it's not constant. It's not it doesn't vary in a constant fashion. There is no equation. So there are set of texture color. So each texture. So I have a quad, and on the quad I have texture. So quad has set of pixels. Texture has set of textures. Each texture has coloring. Now that color is getting mapped. Each texture would get mapped to a pixel. It looks the way it happens. It's a kind of logical. So every texture will get mapped to pixel, but it doesn't happen in the reality. Means texel density and pixel density comes into the picture. If texel density is less, then there will be magnification. And if texel density is more, then there will be minification. So more texel will be mapped to few pixels, or more texel would map to one pixel. In that case, taking the pixel as reference point, then we see minification, we do kind of averaging, that is linear, or we go for the nearest. So that is magnification and minification. Okay, one thing. Second thing is, if I have image, if I have a primitive, means quad is this big, but texture is this big one, then how small texture would go to all the kind of areas in the kind of primitive. So that is another big question. So one is clamping. Like if I have an image and this big board, I have to draw one image, then border it would clamp. Image in the middle and its border, it will clamp to the full kind of a stretching, or it would repeat. Okay, so why this much discussion happening? Because we see kind of lighting and we see texturing. So that was kind of texturing, lighting, and then various kind of shaders. Means OpenGL is straightforward. Means it's very simple if you think step by step. Otherwise, you cannot crack it. Means it's very difficult. Or it is very simple if you think step by step. So, what about shadowing? So, we have seen shadowing, like how we kind of generate the shadowing. So, if I have a kind of image, if I have an object and there is a light source falls on the object, then there will be shadow. Camera is this side. So, camera is looking at the object, light source is here. This side, shadow would form. Okay, so consider the case that, so I think in the tutorial we have seen that how we do the shadowing. So from the light source looking at the object, then we kind of we create a texture image. Okay, so considering the light source as camera and considering the object as kind of the real model, so we use a look at and those kind of utility, so that we bring the light at the kind of center and we do some kind of transformation in the rotation. So, but still, in that way, we kind of do a shadow texture, and that shadow texture in reality means one pass generate the shadow texture, and in the next pass from the real camera we draw the scenery and we take the shadow texture as a reference, and then we check if whatever is visible from the camera should if in mathematics it should not come in shadow. So that is the idea. Now, what is the problem here? Means we have seen the solution and we have seen the shadow icon, like if the texture and pixel density is not same and there is variation, then there is a light shadow, light shadow, light shadow, light shadow. This kind of pattern that we see, and generally it happens when light falls on a surface. So light falls on a surface. So surface normal and light, it has angle. In that case, that shadow icon grows. But anyway, means we have seen the remedy that when we do the mathematics from the shadow texture to the final pass, then we do some kind of offsetting, and then we are able to remove the shadow icon. So this is one story. Next story is that, as we talked about, so when we go for texturing, okay, so when we go for texturing, the area on which we mapping the texture, so that has four properties. One property is magnification, one property is minification. So magnification, minification is nothing but pixel and texture density kind of ratio. So that we saw in shadow icon. But next to that is minification and magnification. So that we have seen. Now, what about if texture and the plane on which texture is drawn, texture is small? Okay, so either we can go for so it's called a wrap S and wrap T. So STR is a kind of texel direction, as the way we have X, Y, Z. So if texture image is small and area to be drawn is big, then we can go for repeating or we can go for clamping. Okay. Now, as I said, that OpenGL is a if we have to think step by step. So, generally, what we have seen in the example, that we use the same frame, same projection matrix. So, the analogy of the camera that comes in the OpenGL. So, there we have model that is kept at the center, and then model is transformed with the model view matrix, and then again it is transformed through the projection matrix. Okay, and at the end we get the window coordinate where each pixel in the model would get drawn. So model is at center, then it goes here and then rotated, and finally it's come to a location, and then Mr. Projection comes into the picture and it does the clipping. Okay, so means in mathematics there is nothing called clipping. It goes for matrix multiplication, and then it cuts what doesn't come in the clipping. So even though we take the projection matrix same as a texture generation and what we see from the camera, so first pass and the final pass, even we take the same projection matrix, it's still model view matrix matters. Means they are different. So if model view matrix for the shadow pass and camera pass, final pass, if they are different, then the shadow texture, what we generate, so that texture, the width and height will be different, because we are using projection matrix, and especially if we are using perspective. So in that sense, it will be different. If it is different, then from the camera, from the final pass, whatever the area on which we are drawing the image, that area may be bigger. If that is bigger and texture is small, then it will come to wrap S and wrap T. So if I set the clampage in wrap S and wrap T, it will stretch. Texture is small. Area on board on which it will draw, it is big, or it has many items. Texture is small. Then it will have stretching, because it has to stretch to fit into the board, right? And if we don't go for a clampage, we'll go for repetition, then it would repeat. Shadow will get repeated. I have seen on kind of internet that there are lots of algorithms are coming. Our model view matrix, the camera model view matrix, even though we are taking projection matrix same, since model view matrix of the camera and light are different, so the window, the way it sees are different. So clipping happens and both are different. So in that way, it is different. So how we can make similar so that there should not be kind of stretching or clamping or repetition. Okay, but we'll see a way that is very different, and how we can kind of remove the kind of this unknown, unlikely clamping or unlikely repetition. Okay, so that procedure hangs in texture unit. Okay, so OpenGL works in a fashion that if I have an image, then image will get status of object. Okay, so image is nothing but it's just byte data that will get a status. Please refer kind of texture tutorial. So that will get kind of status of texture object. So now, since it is a texture object, it will have a data as the image data, and it will have operations. So operations like MagMin, RapS, RapT, and for the anti-aliasing and these kind of things for other factors. So we can have operations. So texture object comes into the picture. Then after texture object, there is another guy comes into the picture. That is called texture unit. Texture unit and texture object, they work together. So what we want means, if I have a set of pixels in the kind of board on which it has to draw, and if I have a texture, it has set of texture, then each pixel will get what color from the texture. That is the final question. Means I won't go for this much kind of discussion, but discussion is based upon it. So if I have a set of pixels, each pixel coloring is simple if I take from the interpolation of the vertex or interpolation of the vertex from the lighting. But what about each pixel color has to come from a texture or set of texture in the blending? Yes, becomes heck. So in that way, OpenGL goes for, even though it is a C function, but it goes for object oriented, and it comes with the two entity called texture unit and texture object. So we say, this is my pixel position. Mr. Texture Unit, can you tell me what is the texture color? Now texture unit, as we see in the shader programming, we say sampler 2D. So that is the texture unit. So texture unit takes the pixel position, and then after that it goes to texture object and say, this is the pixel position. So can you tell me what are the operations you have? For RapS, RapT, or minification, magnification, and then for kind of anti-aliasing and for MIP mapping. So for all those stuff, what functions you have? It uses texture object functions and data, and then it thinks about the actual texture color. Okay, there is means if we go for repetition, okay, then image is getting repeated in the final shader program, and then since we are looking at the near and far when we draw the shadowing, so we go for multiple shadow. That is completely unacceptable, undesirable. So in that sense, we kind of we get the so when we go for final pass, we have pixel, okay, and we have interpolated texture that we in final pass we again generate the texture from the lighting source. This is what we have seen. From the initial pass, from the lighting source, considering it as camera, then we draw the texture. Then in final pass, there are two cameras. One lighting camera again comes into the picture. From there, we go for texture and then interpolated textures. So there, if texture crosses the image boundary, then in that scenario, we generate kind of mathematics that it should not draw the texture. It should not draw the shadow. Okay, so I have a texture. It has to be drawn on a board, and here is a light. Light falls on the texture, and there is a repetition of the shadowing because texture has to be repeated because the OpenGL, the camera vertices are more. I mean, pixels are more. So texture has to be repeated. So if it has to be repeated, I mean, shadowing has to be repeated. In that case, we try to find out what are the area that is away from the texture, means beyond the boundary of the texture. If we are able to find that, then we are not going for shadowing mathematics. Means, boss, please draw it. I don't want shadow. Otherwise, go for shadowing. Otherwise, it was going for shadowing for other areas beyond the frame, and clamping or repetition happens. So let's not go with whatever is kind of we see on the net. So we go with the simple fundamentals, and we can remove these kind of unwanted things that anyway we are getting through the texture unit and texture object. So repetition in the shadowing or clamping in the shadowing. So that means, okay, and we are receiving kind of questions like what app or what software we are using to draw the kind of whatever we are seeing, and in future, like we have promised that drawing will be minute, and later in the future we will kind of attach it to machine learning or artificial intelligence engine, so that we can see more enthusiasm and kind of more generic graphics in social terms also. We will have kind of real life example. Okay, so what app or what software are you using? We are not using any app, and we are not using any software. Okay, so we are using one small, very small Python program, and that is generated locally, and it is not generated internationally. So it is very local. Like we see localization and internationalization techniques when we go for kind of multi-language supporting. So there is no internalization, so it's a local code, and it's a very hardly 3 or 4 functions are there. One is for display and one for handling the keyboard. That's it. And then we see that how it works, that we have seen. So that the small program. Okay, so further the discussion on shadowing glitches. So we'll proceed on desktop. So this is Linux Mint. Okay, so we'll see the concept of the shadowing in the OpenGL, and we'll see the problem, and then we'll see the scenario, texture object and what is texture unit and why it's happening, and then later we'll see the resolution. Okay, so how problem kind of it is arising, so that situation we'll talk. So we have talked in a detail that what is the shadowing idea behind the scene. So if there is a kind of object, so there are models, and if we need to draw these models from the camera perspective, then I can draw it the way it is, but if I want to draw the shadow also, then from the light perspective also, I have to see these models, and then we can draw the shadow. So this has already been kind of explicitly in detail it is covered. So if I consider light as a camera, okay, then light I can bring to origin through some transformation and rotation, And then if light comes to origin, then from light source it would see the models like this, okay, that we can kind of estimate from here only. So if I consider light and the direction in which it is seeing the model, so if I am concentrating on this model, then this is minus z-axis. If this is minus z-axis, then if I transform the light to the origin, then it would see in similar fashion. So if that is the scenario, then I can capture this. Okay, so whatever I see in x and y direction or s and t direction, so that will become a left, right and top bottom, and what we see in the z axis, that would become a depth value. So this is what we are seeing. Okay, so this is the photograph that is taken from the light, and that photograph white means there is nothing behind the scene, so this is the maximum distance, and then gray color is the surface, what we see as kind of orange surface, and then what we see as a blue, a sphere, so that is even near. So this is the scenario that we are saying. Okay, so now from the camera perspective, so if I want to draw it, then for each pixel, so if I take a pixel anywhere here, then for this pixel we'll again calculate the z-axis distance from the light source, and for this pixel that z-axis distance will be compared against the z-axis distance at the same x and y location in the image, and that will have less value because bigger sphere is coming into the picture which has less depth. So in that sense, this pixel would be candidate for the shadow. So this is the analogy that we have seen. So this is become a candidate for the shadow. So we can see the shadow. Okay, what would come as a texture map? So texture map is nothing but it's a raster image which has width and height, and its value is as the depth value. What we see the depth in the z-axis minus z-axis, those value we see. So if it is 1, then there is nothing behind the scene. So this is the GLU perspective frustum. 0.7 means there is some surface, and 0.4 there is something more near to it. That is the sphere, blue sphere that we are seeing. Okay, so same thing we can see. So if I kind of draw a frustum, a GLU perspective frustum from the light, then frustum is like this. Okay, so if I take in the beginning pass, in the texture making pass, so if I consider this frustum, okay, then in this frustum we see the sphere and we see the plane. Okay, now in the final pass again we draw the frustum. So in the beginning pass, when we draw the image, then whatever is near the light source that will come into the image, and far would not come in the image. Like we see the image, what we can see. So all the points that is behind the sphere would not come into the picture. Okay, so that is the shadowing pass. Okay, so while in the final pass, for again we'll calculate the depth value from the light source, and we'll compare the depth value what we see against the whatever the depth value in the texture, and if depth value is more, then it is candidate for the shadow, that shadow we are seeing from the camera perspective. So this is what we are already been seeing. Okay, so what is the problem? So problem is like, if I have a light source and we have a frustum, so this frustum, like if it is a GLU perspective frustum, then frustum has a kind of distance from the light source, and frustum has angle. So if the frustum is exactly same for the camera and the light, still we will see the image differently, and that is differently what we are talking about. That depends upon what is the Z value. So if from the light source, okay, so from light source, if these models are near, then these models are from the camera. Okay, so then we will probably get different kind of images, like what we are seeing now. Okay, so this light source is near to these models, and so these models are coming inside the frustum of the light source. But if I see this as a cone, if I make this as a cone, the lower part of the cone is not coming in the frustum. But whereas since they are distant from the camera, so everything is coming into the picture, even though there is one more sphere that is also coming into the picture. So the picture that is taken from the camera, it is broad, and the picture that is taken from the light, since frustum distance angle is same but distance is less, so less things are coming into the picture. Okay, so it is like what I am talking is, okay, so this angle is same. This is what I am talking. This angle is here and here. This angle is same. So frustum is exactly same. Okay. And but the distance, okay, so the distance from the light source to these models, okay, so this distance is different. To make it more clear, I can bring the light source even near. Okay, now distance is certainly different, so I can say it like this distance is d1, then this distance is kind of d2, so both are different. Okay, so how it makes difference? If depth value is different, then how things changes? Okay, now if I take the photograph, then this yellow color sphere would not come in the light photograph, and then the cone bottom part is also not coming. So in the photograph only this much will come. Okay, so information is missing. Those information are available from the camera perspective, but those information are not available from the light perspective. Okay, so we'll see kind of how actually OpenGL works. So if I have a kind of model, we consider model is always placed at the center. So if model is placed at the center, that means origin of the model is placed at the center. Now at the surface of the model, there is any kind of a point, physical point, that is x, y, z. Now if I do the transformation of the model, then model reaches somewhere in the space and same pixel is x1, y1, z1. Now after that, we apply projection matrix on top of it, and this x, y, z become x2, y2, z2, x1, y1, z1. It is something like, if x1, y1, x, y, z is the point when model is placed at the origin, if I multiply with the transformation, then it becomes xy, x1, y1, z1. Similar as I multiply this with model view matrix x, y, z, then it becomes x1, y1, z1. Again, whatever x1, y1, z1 I receive from here to here, again it is multiplied matrix with projection matrix. It gives us x2, y2, z2. That is different in both scenarios. Okay, so projection matrix is same in both scenarios, but transformation is different. If transformation is different because the minus z value, the depth value, because light source may be near to the model than the camera. If that is the scenario, then camera is able to capture other models also, where light model is not able to capture other model. Only it is restricted to some part of the model scenario.
So the image, like in the real scenario, I have taken the image. See, we can see image, even cone is coming only little bit, I believe not 100%. And so this is the actual scenario. Like if I seeing from the z-axis, then there is a ball, sphere at the center, and there is another wired sphere, a wired cone at some location, and there is a light source. Okay, now from the light source is seeing this wired sphere, and image is coming, wired cone, image is coming here. Since this red ball is not coming in the frustum of this light source is very near to this, so this red spot is not coming in the frustum. If that is the case, then in the real photograph, what we are capturing, the red ball is not coming. It is a black and white image. Only cone is coming. We can consider red ball as this ball, yellow ball. It is not in the frustum of light. If it is not in the frustum of light and it is in frustum of camera, then it is coming from the both view. Now, this is the original view. Okay, first it is taken as what we see the object texture object, we will talk later. So texture object and its attribute. So in that scenario, this is GL repeat. If GL repeat is happening, then this image is getting repeated. If it is a clamp, then it will get clamped. What it is happening? So if the frustum from the light source, these models are near, the image that is getting generated is small. If this image is small, image has to be laid out on the big photograph, then either it would be get repeated, so shadow is getting repeated, or if I set it at GL clampage, it would clamp. This is completely unwanted. We have already removed the shadow acne. Okay. Now that is because of the texel density and pixel density are different. So in that way, shadow acne we get. But we are getting another unwanted thing. That is because of the frustum, the texture what we are taking. The texture is small and texture is forced to repeat in the shadow, or it is getting clamped. So this is another view taken from the x-axis and one view taken from the z-axis. So looking in the minus z-axis. Okay. So certainly we can see the red spot is at center. And there are two planes, yellow plane and there is one kind of gray plane. So they are kept like this. One gray plane and then yellow plane. And then light source is seeing the cone and clamp edge and GL repeat. So this is completely undesirable. Means I cannot have a model which have these many shadows. So shadow can only be one. Okay, since the light source is only one. Okay, so this is a big concept of research and how we can bring the images that is coming from the camera and the image that is coming from the light source. So they should have equal depth. Now again we will go with some biasing and then we'll try to bring it in the same depth. So that is not required. Means we'll see what can be the solution. So this is the actual image from the that we have, that we'll see. So actual image doesn't have even full cone. So red spot is anyway it is going out of the model. So if we can see this white sphere, it is seeing at the cone here, then it is coming out of the projection. So one way is we have to set the angle of the projection is big so that red spot will be covered. So how much we can do? There are limitations. Okay. And so, or we have to do lot of mathematics. So that we'll cover that how we can solve this. Okay. So that we'll see in the concept of texture object and its attribute, and then texture unit and texture object. So that we'll see, and then how photographs are getting generated and how it is getting laid out. Okay, so we'll proceed. Okay, so for clarity, we can see it is kind of more neatly. Now if this is the light source and this is the model, since light is seeing only the model, not this ball, so only the cone, because this is what we are using in GLU lookat. And then this is kind of if we use the clamping or if we use GL repeat while creating the texture, so this would come like this. And if we take the photograph through the light, black and white, so this would come in the photograph. Okay, so this is clear. Means this is kind of from the Z axis when we draw. So this is how. So this clamping is unwanted, and if I use repetition, then this is again unwanted. So this is the actual picture. Otherwise, these are undesirable. Okay. So here, this is actual picture, and this clamping to the edge is undesirable. Okay, so we will see the texture object and its attribute, texture object and texture unit. So what are these? Okay, so when we have kind of image, okay, so when we have image, so image generally it's just a kind of a byte data. So we create a texture object, and inside that we copy the image. So image comes inside the texture object. So these slides are taken from the texture tutorial as it is. So the now texture object contains the image data. So the API that is used is GL text image 2D. Okay, now when it comes inside the texture data, it is something like this. So texture object contains the image data, and then texture object provides various functions, and those functions comes from various interfaces. I mean, this is a kind of hypothetical design that is proposed. Like one interface is where mag and min filter is applied, one interface where GL texture wrap S and wrap T, and then a texture environment and then MIP mapping. So these interfaces are implemented by texture object, and it provides the function like texture filtering, MIP mapping, texture wrapping, texture function, the spectral light. Okay, up to this only. Now, so when we kind of create the texture object, we kind of call a function called GL text image text parameter, and inside that we provide the property for wrap S, wrap T. So like if, okay, like this is kind of a screen and it has set of pixels, and this is the image. So image is small, whereas the screen is big. So we can provide like the property in the texture object as wrap S. So when the image is small and we provide kind of something like when we map the like something like this, like GL text coordinate, okay, GL vertex. So whenever we have a kind of any primitive, and then inside the primitive we have vertices. So against the vertices we provide, like if this is the vertices, this is the vertice. Against each vertices, what is the textual coordinate? So if textual coordinate must be between 0 and 1. If it is below 0 or above 1, then what would be the nature of wrapping S? So like here the screen is big and image is small, then if I provide, so the texture coordinate should be between 0, 0 and top right between 1 and 1. If it crosses 1 on this side and it is below 0 on this side, then in the X side what would be behavior, and then in the Y side what would be the behavior? Okay, so I have to provide through GL text parameter. So wrap as, if I provide GL repeat, then the image which get mapped onto the screen, so that would get repeated, or mirror repeated, or clamp to edge clamping, or we'll say it should be a border. Whatever border color we specify, it will become a border. So that is up to us. Now what is this is the texture object. So when we create a texture object, we first read the image data inside the texture object as image data. Then we set various property like texture wrapping, texture function, specular lighting, MIP mapping, texture filtering. Okay, so we are talking only about texture wrapping now. So in the texture wrapping, if we provide the texel coordinate less than 0 or more than 1, in that case, how in the S direction, how in the X direction, how it would wrap? It would mirror, repeat, or it would repeat, it would clamp, or it would have a border. So here we are seeing a kind of clamping. So here it is clamp. Okay, and whereas here it is repeating. So this is what we have set. So we have set, if wrap S is set to GL repeat, it would repeat the way it is repeating. The way it is repeating, we can say clearly it is repeating. Or if it is clamping, then it would clamp. The way it is clamping, this is what we don't want. So, okay, now if we see the kind of shader code, then we don't worry about the texture object. Texture object, we set this property in the Python code itself, whereas shader code is C code, and there we talk about texture unit or sampler. Okay, so sampler is a guy which takes texture coordinate as input, and then it goes to texture object, and looking at the condition of the texture object for that text coordinate, it would try to fetch the actual color of the at the particular texture coordinate. Okay, so like if I want to have a pixel color at these areas, then it will have a texture coordinate more than 0. So because it is repeating, then it will go and it will say that my texture coordinate is 3, x is 3 and y is 2. Then texture object would see its texture wrapping function and it would say repeating. If it is repeating, then it will decrement, it will bring it back normalized to 0, 1, and it will try to fetch the color of the particular texel. So that would like that. So at the end, we will see kind of repetition. If it is repeating, if it is not repeating, then it would be like clamp to edge. Okay, so this is the scenario. So texture unit is a guy which takes the texture coordinate in the shader programming and then go and it refers to the texture object, and whatever the grammar we have placed in the texture object for the wrap S and wrap T, it is repeat or it is clamp or it is border. According to that, it would estimate the color of the texel at that particular texel coordinate and it returns the color. Based upon the color, we see something like repeated. Okay, so that is the scenario, and then we see something repeated. But if we see the actual texture, okay, we see the actual texture image that is taken from the lighting source, the photograph what we have taken, it is up to this much only. So our image, that, so when we talk about this diagram, okay, so from light source one image is taken, okay, and that image, and from the camera, okay, from the camera another view is there. So from the camera full thing is visible. Okay, so from camera everything is visible, but from the light, so from the camera full stuff is visible. Okay, from camera everything is from left to right, everything is visible. But from the light source, only this much is visible. So we have kind of highlighted in green rectangle, only this much is visible. Now, if we try to find out the mathematics of other area, then it forcefully goes and it repeats, because this is what a texture object we have made like that. Okay, so it is something like this. So this is the model, and this is another model, and this is the light source white. So white sees the model, it is not able to see this sphere because directly it is seeing the model, and then that is a cone. So this much it is coming in the photograph. Okay, otherwise other area is not coming, and they are repeating as per the texture object grammar what we have said. Okay, so what is the solution? Now question arising, what is the solution? Okay, so we'll add a section here. So what is the resolution? If that is the case, okay, so what is the resolution? Now how we can avoid this kind of unwanted thing what we are getting? Okay, now if we see closely, then what we do is, when we are drawing the kind of from camera perspective, when we are drawing the objects, then every object we are drawing and we are referring. So there are two passes as we have talked. One pass is making the texture, and another in final pass again there are from the light source we are assessing the x and y, so kind of indexes in the texture, and then whatever the depth we are seeing, through that we are comparing the depth value, and then whatever we see in the camera, so that we are kind of we are trying to fix the actual value. Okay, so like if I am drawing this cone, okay, so cone is getting drawn neatly because these parameters are near to the camera. But if I trying to draw this plane, yellow plane, then this region are coming under shadow. Okay, because the depth of this region is this region is coming. So if we see the photograph, okay, so if we see the photograph, then whatever we are seeing here, this is actually cone. So this is the yellow. This is yellow plane. So this is yellow plane. This is black and white. So this is yellow plane. On top of the yellow plane, we are seeing the cone. Okay. So on the yellow plane, the region that is coming behind this cone, they will be drawn as shadow. This is not shadow. This is actual blue cone. This is blue. Whatever we are seeing, this is blue. And whatever seeing behind the scene, this is yellow. Okay, so whatever seeing in the actual camera reel, so this is cone. And this is the cone, that is blue. And this is yellow, that is this plane. So, but when we are drawing from the camera perspective, that is staying at 0, 0, 0, then this region would be drawn as a sphere, as a shadow, because it is coming behind the scene of this sphere. So this calculation behind the scene, not the behind the scene, we will restrict only when in the final pass. So in the final pass, when we are doing the light, again we are doing from the light. So at the first pass, we are capturing the texture coordinate. We are actually getting the texture, the image. In the final pass, again from the light source, we are calculating the depth. So this calculation we will do only when this is not available anywhere on the internet. Okay, it can be searched. So this calculation we will do only when in the final pass from the light perspective, when we have S and T, that is inside the texture, inside the image what we have generated. So if it is inside the image, then we will do, if it is inside the image, then we will do the calculation. But if it is outside the image, okay, then we will not do the calculation. Okay, so now we will proceed for the source code, and then we'll see that whatever we are talking inside the image, outside the image, how it works. So that we'll see. So we can start. Okay, so we already have a texture map directory that we have already created. Shadow map. Okay, and these are the kind of, so we can modify this file itself. So I'll remove this and shadow master.txt. So we have only one file, text.py. So this is what we have been seeing in the shadow map tutorial. So I'll just have a copy of it. And wherever it is required, we will modify it. Okay, so we'll have a function called normalize from sklearn. Okay, so probably I can just go through it. So there is a init function, and inside the init function, we create a frame buffer, and then we create texture object, and then we fill the texture object. We load the image as none. So it is a to a frame buffer in a GL depth component as the type of the its image type. So that we set, and then we call frame buffer texture 2D. So its idea is that the frame buffer, whatever the frame buffer is drawing, it should come as a texture and as a depth attachment. So that is the idea, and we have set it as float. So maximum it will go as 1, the depth, and then we draw it, and then in the display first is this is the texture pass, and after the texture pass we whatever is drawn on the texture, so that we push in the image, and then in the final pass we calculate the from the light vector what we showed in the final pass. Okay, so first is a texture making pass. So texture making pass, actually it creates the texture. Texture making pass create the texture. In final pass from the light source we again take the calculation, and whatever S and T we receive, so that S and T we map in the texture with the minus Z as a depth, so that this value then we compare, and then from the camera we actually draw, and in the shader we do the computation. So that is the concept behind it. Okay, so this is the final pass, and in final pass in one go, first from the light everything is calculated, and then from the camera perspective we do other stuff. We reshape, and we set the GLE perspective as 45, and okay, and then we we draw it. So this is the shader code. Okay, so these are neatly explained in the shadow map tutorial. Okay, so we'll modify the code, and first we'll see the problem what we are facing, and then we'll see the resolution. So I'll add from sklearn, because we'll need to import pre-processing. So here this would help in calculating the normal of two vector. Sklearn import pre-process math numpy re pil shadow texture none 256 and okay, nice. I'll add light position rather than kind of hard coding it. So we'll initialize it here only. So minus 15 and 10 and minus 10. So this is light position. And then we'll add cube position equal to 0, 5 and minus 10. Okay, so we'll add a normalize. Okay, so this is the grammar for normalizing a vector. Okay, preprocessing.normalize. So whatever we are getting NP vector, so we convert it to NP array, and then NP axis, a new axis, okay, and then axis is equal to 0. So this is how we do kind of a column by, then we reshape it to 1 and minus 1 and to the list. So this is how kind of we normalize. Okay, so normalization of the pre-processing from the sklearn, it needs a kind of a reshaped vector in this fashion. So once kind of normalization is done, then we reshape it to one row and any type of column. So in single row, so then we take the 0th one and then we tool it. Okay, so these are kind of local code you may not find anywhere. Okay, so that is what it is. So now in init, I don't think we need to change. So GL clear color depth test. So we create the frame buffer, then we create the texture object. We bind the frame buffer, we bind the kind of texture object. Then first we'll see the clamp to edge, then we'll see the repeat, and both should be resolved. So that is the idea. Okay, nothing changed, and then we do frame buffer texture 2D, and then we check for the error, and then we release the frame buffer. Okay, so draw, I'll see if something we see that is different. So that will code. Okay, so along the x-axis we'll make it -3. So wherever the light position is, we'll draw a cube, white cube, and along x-axis it will be -3, so that the cube should not come in the front. So that is the idea, and I don't think there is any change. Then we draw a kind of wire cone. So instead of a sphere, so we will have a wire cone, and we'll try to draw it at the center. So there is no meaning of translate now. Okay, so no, sorry, so that wire cone would be at some location. So GL translate. So rather than hard coding it, so this is why we have pushed a light cube position. Okay, so this is the the place okay, so this is the place where so we'll say kind of cube position. This is this position. So if we see, I believe it is more clear here. So this is cone position, this is origin, red spot, and then this is light position. This is one surface and this is vertically yellow surface. So 5 things we need to draw. So that is the idea. So this is the kind of instead of wire sphere, now it is wire cone. So I would delete it. Wire cone and 4, 10, 32 and 16. Okay, so 4 is the base radius, 10 is the height. Okay, GL push matrix, translate it to -20. So we color it and then a kind of we'll scale it. So we will not draw the table, we'll draw a surface. So we'll scale it to kind of 60, 0 and 60 in X and Z direction, and it will have 1, 1. So this is how it is. Then we have yellow stuff, the vertical one. So color is yellow and we'll translate it to kind of 30, 0 in the x-axis and we'll scale it to 60. Okay, so probably no rotation. We don't need any rotation. We'll scale it to 60, 60. It will be kind of bigger. Y and X direction, and that's it. GL push matrix, GL color, and I believe we are done. So this is yellow stuff. This is yellow plane. Okay, so it is at X 30 and then we scale Y direction. And this is the flat plane. This is down one. Okay, so -20 down, and then X and Z direction it would kind of expand. And then at the center, okay, so this is the cube. This is the kind of wired cone. And then this is the cube position and this is the origin. Okay, so we are done. So we'll change display. So this is the stuff. Okay, so uniforms load shader. Appear GL color buffer bit reshape shadow height mode equal to shadow. GL you look at. So from light position, so this would kind of change west. So now we will kind of so this is the place where we are receiving the error. Means if we look at the sphere, then it is multiplying. If we look at origin, then probably it is not multiplying. This is what we are saying. But if you look at from the light position, if we look, then it is multiplying, and this is required because there was some problem there. So cube position. Okay, so light position, cube position, and then we will change kind of. So light position is where the light is kept, and cube position where it is seen. So this is light position. This is light position. this is cube position, in the sense cone position, and then it will see. Okay, so this is the exact code. Okay, now here we have to do a lot of things, because we need a normal, in the sense that probably I can edit it. Okay, so if it is seeing from this to this in this direction, then the camera should be, the camera up vector should be in this direction. So it is not y. Can we see this? Okay, it should be perpendicular to kind of what we are seeing. So that is issue. So now what we'll do is we'll calculate a plane that would be perpendicular to this first. So if I do kind of okay, so if we know this vector, yellow vector, okay, so if this vector, I think we'll type it first. Okay, it's quite difficult to implement. Normalize NP cross NP cross NP subtract cube position, light position, subtract cube position, light position. Okay, so first we are kind of cube position to light position. We are kind of calculating, and then we are crossing with y-axis, and where it comes, okay, and that we are crossing again with the cube position and light position. So idea is that we take the y-axis, this is y-axis and yellow line. So this, it makes a plane. Okay, so there is a plane that constitute if kind of so this is a plane in that direction. Now if I take cross, then we get another green line that is perpendicular to it. Now green line and yellow line, if I take cross, then I'll get this. Okay, so these are local code, means we have kind of seen this. Okay, so this way we can get this reddish color arrow. This is what we want. We don't want look camera vector in this direction or this direction. This is the direction what we want. Okay, now GLU uniform, I believe it's all right. Load identity and draw. Okay, so we will get the photograph the way it is. I don't think any change is required. And then GL color, and then GL look at. So we'll copy paste here. So look at would change here also in the second pass. Okay, so no more this is the look at. So look at is what we typed here. Okay, from the light, look to the cube and then kind of point in the vertical kind of vector. Okay, so this is how it is. Okay, so GL active texture 0, and then I believe it's all right. Okay, so it's all right. We'll see if we are really able to get output, or we can modify it. It's some bigger, like 100. So from Z direction it would see, and it has 30. Okay, and then it is okay, reshape as 45. Okay, so load shader will keep as it is, so that we can see the defect. Okay, so nothing is required. Now if we are able to kind of reproduce it, then we'll fix it, hopefully. Okay, so okay, so there is no clamp to it, the what I was expecting. Okay, so we'll try setting it. Kind of more near, we'll try. Oh, so light position we are overriding. So we'll try again. Oh, so there is problem. Okay, so we can see that there is clamp to edge. So there is an issue. If we make GLU look at from the light source to the kind of okay, so I can rotate it. I believe it will be more visible. Okay, so instead of here, I can just say kind of GL rotate. GL rotate 90 degree along Y axis, and then GL translate so that it will be little far. Let's try if we can able to rotate it. Okay, it's so we rotated it, and this white is light source. This is the cone. Now clearly we can see if it is pointing, looking at the cone, then it is clearly a clamp to edge. Okay, I can move the light source, so it's prominent. Okay, now we can see that the origin where red ball is there, red ball is also coming into the picture because light source is seeing in that direction and red spot is also coming. But if I move like this, then red spot would vanish. Okay. Okay, so if I put the light source near, okay, so red spot vanished because it is looking only at the cone. So in that projection frustum, red spot is not coming. But if I move it far, then red spot is coming. So it is coming in the frustum. So I believe I can bring it back. Okay, so we can see that red spot is not coming here because it is looking. So if I kind of increase the distance, so if I say increase the distance, then red spot would come because it will come in the frustum. Okay. But if I move it near to the so it is only kind of so these are kind of it is not highly usable. Okay, I can show it with the repeat also. So climb to edge we have seen. Now I can kind of comment it and then I can say GL repeat. So problem would persist and it would repeat. It is repeating. Okay, so that is the concept. So how to avoid it? Either I can kind of see from the large distance, means this is not a solution. Then kind of, so if I see from the large distance, then this image would be big. Okay, so no need to repeat. I mean, this is what I want to say. So if I can make it as minus 35 it is looking. No need. Still problem is there, but it is less. Now it is repeating. So image is big. Whatever image it is drawing, I believe we can see it. Okay. So this big image it is drawing. Okay. Left side is white. This proves that it is seeing the far. So it is crossing the table. Yellow kind of whatever we have this yellow plane. It is from left side. It is seeing crossing the yellow plane. That's why it is coming as white. And then this big image is coming. So we are talking about the image size. So image size is bigger. If image size is bigger, then repetition would not be the way it is like this. Okay. So less repetition would happen. So that we can see that there is less repetition that is happening. Okay. So the image is big. So repetition happens from here. So if I set even bigger, then it would completely go away. Then image side would be kind of so image side would be comparable to the screen size. So one image will come, that's it. That's it. No repetition is required. Means it is far away. So big image is appearing. If we bring it nearer, then the image taken by the light in the texture. So if I see the image, Now if I see the image, then image is very big, pretty big. So no need to repeat it. This is what I am trying to say. So if I bring it near the way we are doing, then repetition is required. Now if I browse the image, so both images are gone. Okay, so this is the image. Now I am not going to close it, and I'll make it kind of a 65, 55. Okay, I'll browse the image again. So certainly, okay, it is bringing in the same image. Okay, so I'll keep it and I'll rename it so that we can bring. So this is 55. Image name is. So this is image 55. Now I'll make it 15. Okay, now I'll check the image again. So there is a difference between these two images. So the camera which is catching the image, so both images are different. That we can see. This is a big image. This is very small. Only this portion is coming. So image size. So since this image is small. Okay, since this image is small, this is pertaining to repetition. Okay, so if image taken from the light source is small and screen is big, then it will go for repetition. If image is big, if image is very big, means this cone looks small in front of image, then it is kind of, the size is comparable to the screen size, and then there is no need for the repetition. I mean, what I am trying to say is, okay, so if this image is big, if this image becomes big, if this image becomes big, it is comparable to the size of the screen, so it will come as full, no need for the repetition. But if image is small, then it is not comparable with the size of the screen, so it will repeat. Okay, so this is one solution. We keep, I mean, this is not a solution at all, but for kind of sake of easy life, or we can make, so I'll make it 15, so it is 50, so error is there. Now I'll go to GLU perspective and I'll change the angle more, like 75, so that it would see many things. Still it is better. We can see that now image is bigger, so it is seeing like this. So I can increase even more. No one stops us. Kind of 90. Okay. So very nice. So there is nothing, no problem. Means little bit is there, but it is far better. Okay, it is far better to this. Okay, this is with 45 angle, this is with 90. So again, image is coming is big. So these are the way kind of we can think of workaround. Okay, so we'll come to the actual solution, what we are proposing. So I'm going to reset it to 40 to 45, and this is minus 15. So everything is nice. Now we'll go to kind of shader code. Okay, first I'll show problem is there. it is repeating. Now I'll go to shader code. Okay, so if we see the shader code, in the shader code, we calculate the distance from the light. So whatever the texture 2D, so we are talking about texture unit. So texture unit is a guy which takes texture coordinate as input and then return the color. So here in the shader code, if you see, texture 2D is a kind of API which takes the shadow map. Shadow map is the texture unit. Where is Mr. Shadow? Here. Shadow map is a sampler 2D. Okay, so in the code, if I search shadow map, okay, so we are using kind of texture unit as 0. So GL active texture 0. So that 0, okay, so shadow map we are setting it to 0. So 0 is the texture unit. There are many texture units that we can use kind of for the blending kind of series of texture unit we can use for blending functions. So here we are using the 0 one. So now, so sampler 2D, so texture 2D shadow map, or we can use simple texture also, I believe it should work. So shadow map is the texture unit, and we are passing the shadow coordinate that we are receiving from the second pass as ST, and whatever comes the value in the texture. So texture, whatever we are getting, these textures are nothing but they are depth value in float. Okay, so they are depth value in float. I believe we have shown it many times. Okay, so I believe I can show it again. So raster text. So I'll draw it again. It will take some time. Okay, so it is not taking a texture. So we'll check the version. We have not used the version. So compile shader. Okay, so I'll use the version. Version we can take 140, then it would support texture also, not require texture 2D. Let's check. Version 140, so it should come. Okay, so alright, it took some time, but I believe file is ready. So this is the file, this is the image file. Okay, so it is nothing but the distances in 0, 0, 1, 1. So okay, now okay, so texture map shadow coordinate ST if we pass, then whatever we receive the value, so that depth value we take. So this is the distance from the light source. So this is the okay, so this is the distance what we are getting from the nearest sphere. I mean, this is clear. Okay, so now I am going to set it as a fixed. So float distance from light equal to 1.0. Okay, so this is the fixed distance we are taking, and I am not going to calculate this way. Now I would say if shadow, okay, so believe I can copy paste. Okay, now whatever the distance we are calculating from here, okay, so that distance will manipulate in other way. So shadow code dot s is less than 1.0 and shadow chord dot t is less than 1.0 and shadow chord dot s greater than 1.0 and shadow chord dot t greater than 0.0. If this is the case, then please go ahead and do the okay. I removed it, then I put it again. Okay, no problem. I'll put it here. Okay, so distance from the light is kind of, this is the way we are calculating. So now what we see here in this solution. So this is the solution. Okay, first distance from the light, whatever the distance we are calculating here, we initialize it to 1. So maximum distance. And now if shadow chord dot s, so now in the second pass, so in the second pass from the light, we calculate the S and T, and then we see in the kind of texture what is against the S and T, what is the depth value. So if shadow chord dot S less than 1.0, T less than 1.0, greater than 0.0, T greater than 0.0. So what we are trying to do here is, whatever mathematics, okay, so here if it is inside this from 0, 0 to 1.0, if it is inside this, then only like here we are doing calculation for the full screen. Means this is the screen that is seen by the camera. Can we see the big screen? And whatever we see inside the green, this is the seen by the light. So this is the image that is being captured. So that is this image. Okay. So then we do the calculation against the image. So calculation would happen only when it is inside the image. If it is coordinate is outside the image, I consider it as external. So fixed is external. 1. If it is inside it, then only we modify the distance from the light. Otherwise we don't modify. Earlier we were modifying for everything. And this texture that was returning the color. Okay, so texture unit, if we specify the texture coordinate, then it returns the color. So texture unit, this is the texture unit. If we specify the coordinate, then it returns the color. Color is nothing but the depth value that we are receiving. Everywhere we are returning, and it is duplicating as per the nature we have set. Here in the texture object we have set it repeat. So it is repeating. It is going there and it is checking. So this is the kind of this is the texture unit. Shadow map is the texture unit against all the S and T. If it is beyond the image, then it goes to texture object, and it does, means this is what it is doing. Texture unit, if it receives the texture coordinate, then it is checking the texture object and then taking the texture wrapping, and then it does the grammar that we don't want. So we want do all those stuff only when you are inside the image. Outside the image, consider it as 1. That's it. Okay, so this fix took time. Means it looks very straightforward, but this fix took time. Now it is kind of if depth projection is greater than 0, and then we go ahead with the whatever calculation we are doing. So if it is 1, if distance from the light is 1, then certainly it is not less than this. So in that case, okay, it is 1. If this is 1, then there is no shadow. So around this image, we are forcing it to be no shadow. Shadow calculation is happening only when we are inside this image. Okay, so if distance from the light is fixed 1, it is never going to be less than shadow coordinate -1. In that case, it is 1. Otherwise, it is 0.5. And this is what we will calculate. So we'll try now. Means we have done all the engineering. So we'll try now. Nice. Okay, so there is no kind of repetition. Okay, it is taking time because we are saving in the. So we will not save always. I think it's clear. Okay, so we will not save. Nice. So crystal clear. No error. You can do whatever you want. So nice it is. Nothing. No problem. Amazing. If we are increasing the distance, the red spot is also coming. If I am decreasing the distance, okay, so nice, no issue at all. Okay, so I'll try with the climb page. We can see everything is intact, -15, and GLU perspective is 45. Okay, so I'll see the climb page. That should also vanish. I shall comment this repeat. No problem. It is like a rock solid now. No error at all. Amazing. Okay, so kind of, there is a really bug if I don't fix it. So that I'll show and then we'll close. So I'll comment this. I'll uncomment this and then I'll comment this what we have done. So this is what the change is. So distance 1. So everywhere now it is calculating. So this mathematics we are not doing. And then we'll try if problem persist. Problem persist. Okay. So there is clamping in the edge. If I see clamp edge instead of repeat, then there is a repeat. Glitches in OpenGL shadowing. So that we saw means if I kind of don't consider the texture based shadowing also, then still means we have to know the pixel density, screen size, then all the transformation matrices, and then matrix multiplication. Still means anyway matrix fundamentals that anyway we need to know. But this much information is required. Now if I go for texture based shadowing, then texel density, pixel texel density relationship, so that information is required. Now beyond that, if I go for texture kind of shadowing, then as we saw that means frustum kind of knowledge is required. And then if we come inside the texture, then texture object and texture object creation and what attributes it required, what functionality it provides, frame buffer, and then finally texture unit. So how texture unit does the sampling of the texture, and then it returns the texture color based upon the texture object property. So that we saw. Means as kind of repeatedly I am saying, like OpenGL is very easy if you understand step by step. Otherwise it is completely kind of uncrackable, opaque substance. So means you will land up mucking your hand here or there, and you will spoil weeks, not days. So that is the concept. I mean for any complex programming, step by step knowledge is required. But I mean I am thankful to kind of Python kind of languages where you don't carry any headache for matrix multiplication or any kind of you do the computation. Everything is available. Means you can do kind of you can save 10 times line of code that you do with other programming languages. You don't worry about polymorphism, you don't worry about data typing, and don't ever worry about kind of many functionality like file handling and those kind of things. So anyway, so far so good. I hope that no more glitches come. So whatever glitches we saw in the texture mapping is kind of shadow acne. So that we nicely we removed when we understood the texel pixel density relationship. So that would come in texture filtering. So what we do in mag and min filtering, so there we kind of hit. So that comes under great shadow acne. But if we see the repetition and clamping of the texture shadow, I mean if texture is texture what we generate in the first pass is smaller to the actual screen, then it may go for the shadow acne, it may go for a clamping or a repetition. So we saw that if texture image is smaller, considerably smaller to the screen size, then we did not do our kind of a smart mathematics if computation is happening outside the texture. So all the mathematics we do only inside the texture. So beyond that we consider that length is 1, means it is infinite distance behind the scene. So we don't do any shadowing at all, and this is how we kind of control it. So that is the scenario. So we kind of bind up the texture shadowing glitches, and let's hope that nothing should come up, and then we'll have kind of bright videos, and I'm very hopeful to kind of implementing social media or social kind of 3D graphics, and that would kind of incorporate machine learning stuff also, like automatic 2D to 3D graphics what we see, and then automatic automation, so those kind of thing. So that will include. So that's what we'll see.